and getting into the groove. A screen that says that. Okay, cool. So here's what we're going to try to do today. We are going to go very quickly. You already read this on the D2L. I don't want to belabor it. We just want to make sure that we communicate in a very civil manner, that we all are nice to each other. And we're going to have time to work on that Desmos activity, average rate of change to instantaneous rate of change. So you have time like we usually have in class. And we're going to share a new Desmos activity about beginning with rational functions, okay? So that's our plan, which is pretty simple. And then we're not going to do that yet, but let's then, I'm going to share my screen and I'm going to go to the home page and I'm going to show you what you see as students. So this is what you friends see. Please, if you haven't, and I know it's a bit lengthy, I do need you to read these very well so that we are keeping a cool environment and we have a lot of fun. But in addition to these message about how we're going to communicate, I'm going to share with you some things that you may know already, but if you don't, these will save you time. I have done a few things for you just because I like you so much. One of the first things you'll see is this. Here, I put the assignments that are going to be included in the midterm mark, okay? And so there's 5 assignments plus observations and conversations that I made when we were together up to our last class, which is March 11. And just because I'm such a nice guy, if you click on any of these, it takes you to the assignment directly. So you don't have to go to the assignment and stuff like that, okay? So this is the assignments that are going to be included on the midterm. I mean, we're going to keep working on other stuff. And as you know, I was working on the weekend grading stuff, and I'm already all caught up to the first, I guess, 3. And then, so not everybody has submitted the boxes and polynomials, so please do. And then the average instantaneous rate of change you are working on today. If you look in the calendar-ish here, I have moved the due dates to April 17, okay? All of them are April 17. I cannot go beyond that because I have to produce your grade. But you've had a lot of time. And I'm opening them up again, okay? So I don't want you to be stressed, but I do want you to please go work on them. And by the way, if somebody has a question right now, I'm gonna go back and then we're gonna discuss it. So same thing, if you, for example, are going like I'm not sure about these Desmos, so then you can come here. If you click on it, it takes you to the assignment. And it takes you here, if you click on it further, it takes you directly to the assignment. Like seriously, all you have to do is join, okay? So I just want to make sure that life is the easiest possible for you so you can actually spend time working on what matters, okay? So you have all these here and you have the whatever is going to be included. So I just wanted to mention these to you so that we're all cool. I can see what assignment you have submitted or not, and you are getting feedback on your evidence record. All of them are updated as of yesterday. And so my next homework is to catch up on the polynomial boxes that that many of you have submitted. So that's the next thing I'm evaluating, and then this assignment we're working today. So thanks for listening. So if you now please go to our Desmos average and instantaneous rate of change, and once you get there, please give me a thumbs up. And this is what everybody's saying, that these two gradually, as these guys get very, very close, the slope of this line, it gets very close to 0. Yeah, I agree with that. But now I want you to notice something. Keep your eye here, Mr. Braden. Take a look. Look what's going to happen when I overlap the 2 points. Do you see what happened? the line vanished. I don't have a line anymore. When the 2 points overlap, the line vanished. So here it is, and then it overlaps and it disappears. So here is the question for you. Why did the line disappear? I agree the slope is 0, but when I put it there, I don't see the line. If it's 0, shouldn't I see the line like parallel to the x-axis? Okay, so I'm getting some answers here. Anamish says because it's the same point. Kirushika says, is it undefined? No. Marcus is saying it would be 0 because rise over run is undefined. 0 divided by 0 doesn't equal 0. And Amish says there's no rise or run. It disappears because the run equals 0, says Suzanne. Anything divided by 0 is undefined. Braden thinks is undefined. So we're kind of onto something. There's something that is dividing by 0. Well, guess what? You're right. So let's see what the situation is. Did I share did everybody see the screen that we were before? Yeah? Maya, can you give me a thumbs up or something? Okay, good. So where did this come from? Where did this line come from? Well, the line came from this equation. You see it? Right? We have the slope. This is really y equals mx plus b. This is m, and v is another way to figuring it out, and it's here. And what you said is correct. When b and a are the same, that means we're doing whatever value minus itself, we have a denominator of 0. This is exactly where calculus begins, because this is the problem that some of the people like Newton had, where we're going like, I need these things to be as close as possible to each other, as close to 0, but then when it goes to 0, I can't divide by 0. And so then other concepts came through, like the limit, and later that became the derivative. But in our case, your thinking is correct. So here's the final answer for this. The line exists. We cannot see it because the construction we made doesn't allow us to see it, because we're approximating. So we can approximate, meaning we can get as close as we want, but we won't be on top of it. So we can speculate that we can see this is going to go to 0. I can see it, but then when we get to 0, it disappears. So we are approximating the instantaneous rate of change by getting the points too close. We're not finding it, we're approximating it. That's the key idea of these task. Okay, so I'm gonna show you the next task that we're gonna be working on. So I'm gonna go to here, and I'm gonna go to the D2L, and then we have the next one, which is Desmos rational functions exploration. So this is the next task after we finish this one. And this activity is already there. So if you want to go on it, I'll let you go on it, and then we'll play with it for a few minutes. We'll talk a little bit about it, and I'm going then to wrap it up. So I want you to go in this new activity, and then we can talk a little bit about it, so you kind of have an idea where we're going with it. Let me go back, see my screen. If you're not sure where to go, if you go to the home page, you can go in 2 ways, or 3 ways. You can go to assignments and find it there, or you can just go here and click, and that will take you there. So both of these are good. So when you do this, it takes you to the assignment, and it says here, click here to go directly to the activity, and it will take you there. Okay. Okay. Is everybody seeing the Desmos screen? This is kind of my Desmos screen with everybody's work. And I'm going to shuffle things around. Okay. So let's just, I'm going to pause the Desmos for a moment. Don't hate me too much. Okay. So we're not in Kansas anymore, Toto. we're going to begin to explore different types of functions, right? Many of you are familiar with them already. These are rational functions. And rational functions come from dividing two polynomial functions. So if you go to the first screen, we have a number of terms that are important for this. A lot of things you know. Something that is new is this term of asymptote. What the heck does that mean? And well, the definition is here, very simple. An asymptote is a line that a function gets very close to, but it never touches. So we have a vertical, horizontal, and sometimes oblique asymptotes. A vertical asymptote is one that is vertical, and horizontal, one that goes horizontal. So this is kind of the new concepts here for some of you who are new to this. Here's the definition of a rational function. The quotient, dividing one polynomial function into another. All the other terms we're familiar with. So let's take a look at this. This is our basic reciprocal function. So it's 1 divided by x. And somebody already graphed it here. Let me see if somebody else has a little bit more. No, you just started. So here it is, right? And then we look at what happens with this graph. And some of you are familiar with this type of graph, but some of you are not. So I'm just going to run through this very quickly. Let's think of the first few questions. Question 1a. What happens to f of x as f of x approaches 0 coming from negative values? So this is what we're doing. We're coming here from negative values. X is getting smaller. Take a look at the value at the second value, yeah, at the y point. So for example, here is negative 0.211, and then as we get close to 0, now it's negative 2.155, negative 4, and we can see that this is getting increasingly more negative. Yeah, we can think if we go on forever, it goes to infinity. It's not going to touch this because we can divide by 0. That's kind of where the asymptote comes from. So when f of x approaches 0 coming from negative values, what happens to what is the function approaches what? Positive infinity, negative infinity, 0. I just want you to think of it like that. And conversely, what happens to f of x when x approaches 0? Now I'm coming from here, from the right. You see that? Look at the second value. X is 5.3. The function is 0.18. And all of a sudden, our function begins to get big, very big, right? Very quickly. As our x gets very small, our y gets very, very big. So that kind of takes us there. What we're going to do in this activity, which is kind of interesting, we're going to be connecting this function, y equals 1 over x, with its reciprocal, which is the classic linear function, which is y equals mx plus b. And then we're going to play with those and see what is the connection they have. There's a connection between them that we're going to explore as you do this activity, and we're going to be debriefing. I just wanted you to kind of look at it for a moment. I'm going to give you another 6 or 7 minutes to work on it. We'll pause, and then we have questions. Then we'll